Stage 2 of model-based inquiry is where the unit truly comes alive. This is the first stage students directly experience, and it launches the collaborative sense-making work that unfolds across the entire unit. In this stage, teachers introduce the anchoring phenomenon and driving question, elicit and make public students' initial ideas about the phenomenon, and support groups as they construct their first explanatory models. The focus is on generating as much thinking as possible, ideas, questions, assumptions, and hypotheses rooted in students' everyday experiences and prior knowledge. Underlying this work is a core assumption. Students' ideas are resources, not misconceptions to diagnose or fix. The purpose of eliciting ideas is to surface the intellectual raw material students will use to make sense of the phenomenon over time. On this first day, we don't signal what is correct or incorrect. That refinement comes later as students work with evidence in Stage 3. In this video, we'll explore how Stage 2 unfolds through two high school examples, the Hindenburg Chemical Reaction Unit and the Lamsilis Muscle Evolution Unit. Eliciting ideas about the phenomenon typically spans 1 or 2 class periods and has 3 central goals: introducing the anchoring phenomenon and driving question, eliciting and making public students' initial ideas, and supporting students as they construct their initial models of the phenomenon. These ideas do not need to be complete or scientifically accurate. Stage 2 surfaces what students already know or wonder so that subsequent evidence-based tasks can build from their thinking. In the Hindenburg unit, students watch dramatic archival footage of the airship igniting and burning in under 40 seconds. The teacher pauses to highlight observable details, where ignition begins, how flames move, and how rapidly the sequence unfolds.
I'm going to give you guys a little bit more information about some things that happened this day that are going to be important for us to be able to explain this particular tragedy. So I just passed out your initial thoughts handout, which is where you guys in a little bit are going to have some individual time to write down some of your hypotheses and ideas. But for right now, go ahead and flip over to the back, okay? And just down here, this is all extra paper. So as I go through and tell you parts of this story, maybe you want to jot down a couple things to just remember for when you guys are going to come up with your ideas individually.
This leads to the driving question: how and why did Hindenburg burn so rapidly? Students begin making sense of hydrogen, sparks, weather conditions, and flammable materials long before they encounter formal evidence. In the Lamsilis Muscle Evolution Unit, students encounter a striking biological phenomenon: freshwater mussels with lures projected from their shells that mimic small prey fish. Students examine images and short video clips showing lures with moving tails, eye spots, and coloration that convincingly resemble live fish. This launches the driving question: how did Lamsilis mussels develop lifelike, fish-mimicking lures over time? Students begin connecting the phenomenon with their current ideas about evolution, natural selection, survival, and animal behavior. These early ideas, whether complete or not, form important raw material for the sense-making ahead. After the phenomenon is introduced, students share their initial explanations in small groups and then with the whole class. The teachers record all ideas on a public document called the Initial Hypotheses List.
Okay, and we're now going to move into this time when we start sharing out some of those individual ideas to generate our class hypothesis list. Okay, and remember how this class hypothesis list, we bring this up multiple times during this unit, and we change things or we reword things once we've learned the correct content for what particles do, and we kind of adapt our model for what we think's happening. Okay, and it's fun to watch that change. So please, today, you have an idea, be comfortable sharing it, knowing that it's probably what? Probably wrong, that's okay, that it gives us a place to start, and then also lets me know, okay, so we have these ideas. What activity or task could we do to help figure out if that's what's going on here?
In the Hindenburg unit, students propose ideas such as hydrogen leaks, static electricity, electrical wiring faults, flammable coatings, and weather conditions. The variety of ideas gives the class a broad landscape of mechanisms to investigate. In the Lampsilus muscle unit, students suggest explanations related to predator-prey interactions, selective pressures, survival advantages, life cycles, and heredity. Many students begin with intuitive or anthropomorphic reasoning, such as mussels trying to look like fish. These ideas, even when scientifically inaccurate, are essential resources for future reasoning. Our job in this stage is not to evaluate or correct. All ideas are welcome. Next, groups construct their initial models of the phenomenon. These models visually capture their current thinking and are revised later in the unit. In the Hindenburg example, groups depict the airship's structure, possible ignition sources, hydrogen mixing with oxygen, or imagined sequences of events. Some models are scientific, others are speculative. This is exactly what we want. Teachers encourage labeling, sequencing, and clarity, asking questions like, where is the hydrogen in your diagram? How is the spark being produced?
What should happen, or could you draw right here to illustrate that's what started this reaction between the fabric and the hydrogen gas?
In the Lampsilus muscle unit, groups draw mussels, bass, parasitic larvae, and the fish mimicking lure. Some models show simplified life cycles, others attempt to illustrate how a lure might attract a bass. Early models often reflect teleological or intentional reasoning. These ideas are productive starting points because they can later be reshaped through evidence. The goal here is not accuracy, it is to make students' thinking visible.
Would you show the mantle being extended on this one or no?
Extended.
Gotcha.
These initial ideas become material students will work with, test, and revise during Stage 3. Groups then share their initial models with the class. This step is essential because it dramatically expands the set of ideas available for sense-making. Instead of working with only their own group's reasoning, students now encounter a broad range of possible mechanisms, explanations, and representations. We recommend a modified gallery walk. One member of each group stays to explain their model, while others rotate to examine their peers' models. Students give feedback, compare approaches, and gather ideas they might incorporate into their own explanations. After the gallery walk, groups reconvene to revise their models. This revision is not about correctness. It is about integrating insights, strengthening explanations, and preparing the class for deeper investigation. Stage 2 establishes the intellectual momentum for the entire unit. Students' initial ideas support motivation and ownership, give teachers insight into prior knowledge, and provide the baseline for revisions as students work with evidence. When students compare their final explanations to their initial models, they see how much thinking has developed and why evidence-based reasoning matters. Stage 2 is where curiosity becomes inquiry. By eliciting students' ideas and supporting them as they create initial models, we prepare them for the deep evidence gathering and reasoning work of Stage 3. Throughout the entire process, we treat students' ideas as resources. Every idea, accurate or not, becomes material for reasoning, negotiation, and revision. Stage 2 lays down the intellectual raw material that students will transform as they investigate the phenomenon. To explore more examples or access MBI templates, visit modelbasedinquiry.com.